So hi, I'm Mehtaab, and I'll be discussing oblivious online vector balancing. And the work I'm discussing today is joint work with Brian Alweiss from Princeton and Yang Liu from Stanford. So one of the most famous open problems in discrepancy theory is the Kolmos conjecture. So in particular, you're given unit vectors v1 through vt in Rn, each of unit norm, and you want to pick signs epsilon1 through epsilon t such that the sum of epsilon I vi has L infinity norm at most a constant. And the Kolmos conjecture suggests that you can always pick signs in this manner. Unfortunately, the Kolmos conjecture is not known, and the best known bound is of order square root of log n due to work of Banashik. However, this original work was not algorithmic, and this has been made algorithmic due to works of Bunsel, Dedouche, Garg, and Bunsel, Dedouche, Garg, and Levet. And in general, algorithmic discrepancy theory has been an active field. In particular, there's famous works of Bunsel and Lovett-Mecca, which made Spencer's 6 standard deviations suffice result algorithmic, and there are numerous applications to, let's say, randomized controlled trials and online NV minimization algorithms. The variant of vector balancing we'll be focused on is online vector balancing. So here you're first presented the vector v1, you assign a sign epsilon1, and only after you've assigned your first sign do you get the vector v2, and so on. And the goal, instead of just maintaining the final discrepancy, is that you look at each prefix, so in particular the sum of epsilon I vi up to some point, and you want to minimize the L infinity norm of each partial sum. And we'll call this quantity informally the discrepancy. So let's just walk through one example. So for example, you're given the vector -1, 1, 1, -1. If you assign it the sign 1, then the current partial sum is -1, 1, 1, -1. Then if you're given the next vector, -1, -1, -1, 1, only now do you assign the second sign 1, and now your partial sum would, let's say, be -2, 0, 0, 0. At this point, your discrepancy is 2, and this is just an example walking through a specific set of 5 vectors. And just to show how subtle this problem can be, let's say you just for some reason picked the signs 1 for all 5 of these vectors. Then the first coordinate would be -5, and you have discrepancy 5, versus the choice of signs here gives a discrepancy of 2. Now, in this broad framework, there turn out to be several different models. So the easiest model to understand is the stochastic model. So here your vectors v come from some fixed distribution p, which you know a priori. So this is known to the algorithm. The most difficult model is, let's say, the adversarial model. Here, the adversary gets to choose vectors depending on the signs you've already assigned. So you've assigned the first j signs. Now the adversary looks at what your current partial sum is, and what they can do is they can feed you an orthogonal vector. And because of this, you sort of, if they feed you an orthogonal vector, there's very little you can do. And so it turns out for this reason that the adversarial model is not that interesting a model. Instead, the strongest adversary that's interesting is the oblivious model. Here, the adversary decides the vectors beforehand, and the adversary doesn't get to change the vectors based on the randomness used in the algorithm. And so here, so the relationship between the model is the adaptive is the most general and the uniform is the least general. And you have a square root t upper and lower bound on the discrepancy you can achieve in the adaptive model. And due to works of Bunsel, Spencer, Jiang, Kulkarni, and Singla, and Bunsel, Jiang, Singla, and Singha, there were non-trivial results for the uniform and stochastic setting. By uniform here, I just mean each vector is uniform on the sphere of radius 1. So they achieved a log t bound for the uniform cases due to Bunsel and Spencer, and then there was an n to the 3/2 log t bound due to Bunsel, Jiang, Singla, and Singha. And note that the stochastic and uniform model doesn't have an obvious relation to the offline vector balancing, e.g. the setup for the Kolmos problem, but the oblivious model generalizes the offline vector balancing problem sort of in a trivial way. And the main result of the paper is a logarithmic bound for the oblivious and stochastic settings. So in particular, you can get a log nt discrepancy. And I should note that polylogarithmic bounds were achieved simultaneously for the stochastic model by Bunsel, Jiang, Mecca, Singla, and Singha. So before giving the algorithm, let's just have some rough intuition of what it should look like. Well, first, the algorithm is always going to be randomized because you need to avoid the square root t lower bound coming from the adversarial setting. And if your algorithm isn't randomized, you aren't avoiding this lower bound, even in the oblivious setting. Second, although this discrepancy is not really rotation invariant, all previous analysis of the Kolmos problem were based on some Gaussianity. And so a natural starting point is, let's say, okay, the algorithm is rotation invariant. And finally, this is an online problem, and there's sort of only two things that seem to matter: your current partial sum and the vector you're just presented with. And so let's say that the algorithm doesn't depend on the history, but only on the current partial sum and the next vector you're given. And given these constraints, the algorithm is essentially the simplest thing it can possibly be. So what you do is you maintain a current partial sum wi, then you choose to add the next vector vi plus 1 with probability 1/2 minus the inner product of your current partial sum and the next vector divided by some constant 2c, which is like log nt. And otherwise you assign the sign -1. Note that in this algorithm, I have a failure condition if the inner product between my current partial sum and the next vector is too large. And that's just because the probability I wrote down is not a 0, 1. Furthermore, let's explain where this negative sign is coming from. Well, if your current partial sum is in some direction and you get a vector which is very aligned with it, you sort of don't want to go in that direction, because adding that vector to your current partial sum sort of increases the length. So you want to sort of go in the opposite direction with as high a probability as you can. And that's why there's a minus sign. And the main theorem is that this works. So with probability 1 minus delta, this maintains a discrepancy of log nt over delta. And during the last 8, 9 minutes I will basically be able to give a full proof of this, modulo some easy details. So the key idea is the following notion of spreading. It's not so novel, but this is the framework we'll adopt. So you're given a random variable y in Rn, and you say y spreads a random variable x if there's a way to couple y and x such that the expectation of y given x is equal to x. So in particular, why is this called spreading? An equivalent notion is you sample x, then there's some way of looking at your point x, adding mean zero noise, and getting a distribution, which is y. So spreading satisfies some obvious properties. It's linear in the sense that if y is a spread of x, then for any fixed linear transformation m, my is the spread of mx. It's transitive. If z is a spread of y and y is a spread of x, then z is the spread of x. It's convex. It has certain convexity property. So suppose y is a spread of x, then for any convex function phi from Rn to R, you have the expectation of phi of x, where little x is sampled from capital X, is less than the expectation of y sampled from big Y of phi of y. So why is this true? This is just Jensen's inequality. You basically use the definition in Jensen. This is what falls out. And finally, you can spread bounded random variables by Gaussians. So in particular, suppose x is a real valued random variable, which has mean 0 and is bounded by c. Then it's spread by a Gaussian of variance c squared, in particular pi c squared over 2. So this is a little bit abstract of a definition. Let's give an example. So suppose you have two PSD matrices A and B such that B is greater than A in the loner order, then N0A is spread by N0B. And the proof is just to note that N0B is equal to N0A plus an independent N0B minus A. So in particular, you can first sample N0A and then sample the mean zero noise N0B minus A. So in particular, this establishes that N0B is a spread of N0A. And for general spreading, the mean zero random variable here that I chose, N0B minus A, doesn't depend on the initial sample of N0A. But in general, it can differ. And that's sort of the power of phrasing it in this way. So in order to give the proof, you need a few definitions. So let Wi be the position of the partial sum at time I. So this is just the sum epsilon1 v1 plus epsilon2 v2 up to epsilon I vi. Note that the algorithm fails sometimes, so I'm going to sweep that under the rug. I'll explain how to deal with that. Then, because this function is linear, this probability of going +1 or -1 is linear, you can just explicitly calculate the expectation of wi plus 1 given wi. In particular, if you do the computation, it's I minus C inverse vi plus 1 transpose times wi. What this matrix is isn't so important, but note that in every direct, it's sort of less than the identity in the lower order. So you're sort of, in expectation at least, contracting the vector towards the origin. But this is not deterministic. In particular, you don't always contract towards 0. And so this naturally suggests writing the process as wi plus 1 equals the expectation of wi plus 1 given wi plus some random variable, which is r of vi plus 1 wi times vi plus 1. So basically, I'm just doing a mean and variance decomposition in some sense. And if you write it out, you get I minus C inverse vi plus 1 transpose times wi plus r of vi plus 1 wi times vi plus 1. And now, if you just do a direct computation, it turns out that r of wi vi plus 1 is 1 plus C inverse wi vi plus 1 with probability pi plus 1, and minus 1 plus C inverse wi vi plus 1 with probability 1 minus pi plus 1. This is just the inner product of the two vectors. And note, this gives you a sort of easy way of defining what wi plus 1 is if the algorithm has failed. You just set it to be 0. And note, just by sort of construction, if the algorithm hasn't failed, then this identity wi plus 1 equals this sum of two random variables actually captures the true position. Furthermore, by construction, it follows that the expectation of r of wi vi plus 1, even given wi's mean 0, and since the algorithm hasn't failed, we have that the inner product of wi and vi plus 1 is bounded by c. So this is a bounded random variable. It's bounded by 2. And so the main lemma is that there's an appropriate Gaussian, in particular n0 2 pi ci, which is a spread of wi at all times. And given this lemma, the proof of the main theorem just follows by standard properties of some Gaussian random variables. So let's just say it once again. So what you do is you write wi plus 1 as the expectation of wi plus 1 as the expectation of wi plus 1 given wi, plus a random variable r of wi vi plus 1 times vi plus 1. And so you have this decomposition. So now the proof is basically just a two-line induction. So recall that r is mean 0 and always supported on minus 2, 2. And so because of this fact that you can spread bounded real random variables, you can say that r of wi vi plus 1 is spread by n0 2 pi, even given wi. Furthermore, by induction, you have that wi is spread by n0 2 pi ci. So this linear combination of I minus C inverse vi plus 1 transpose times wi is spread by the Gaussian n0, this ugly matrix, times 2 pi ci times I minus C inverse vi plus 1 transpose. And so this is a spread of this expectation of wi plus 1 given vi. Furthermore, it turns out in this case, you can just add them. Therefore, it follows that wi plus 1, which is the sum of this initial term, plus r times wi vi plus 1 times vi plus 1, well, it turns out just spread by this Gaussian, where you add the variances. And to finish, you just have to, it's an elementary inequality that this variance is bounded by 2 pi ci. And so now you're just done by induction. And that's essentially the whole proof. So in particular, this algorithm gives logarithmic bounds for the online Comosh problem against oblivious adversaries. And just to recall, the algorithm is pretty simple. You're just choosing signs as a linear function of your current partial sum wi and the next input vector vi. And this analysis was based on the concept of spreading. And the main open problem is, can you achieve an algorithm which gets a bound of a square root of log nt? So we got a bound of log nt. And the best known bound on Comosh is square root of log nt. And it turns out in the online setting, you can't really do any better. You can't, there's a lower bound with no log. And in recent work with Ashwin Sa and Yang Liu, we can get this bound with the slight defect that instead of having plus minus 1 signings, you have plus minus 1 and then a plus 2 signing. So instead of just adding either plus minus the vector, you can also add 2 times the vector. So this probably exists, but we don't know how to show it. And the paper is available on the archive. And thank you for your attention, and any questions?
Thank you. Let's thank Mehtaab. And now I'd like to take any questions, and you can enter them in the chat and I'll read them out. We have about 4 to 5 minutes of questions. The first question is, can you hope to get a constant sub-Gaussianity?
So this is like root log NT sub-Gaussianity, and the recent result is you can literally maintain like, you can maintain root 2 sub-Gaussianity with plus minus 1, 2 signings. So yes, the answer should be yes, but I have no idea how to prove it.
So yeah, thank you for the invitation and for the organizers for setting this conference up. So yeah, I want to talk about 2 problems that I like a lot. They're very simple to state, but there's an exponential gap between the upper and lower bounds in each problem. So for the first maybe 7 minutes, I'll talk about the problem trace reconstruction. In the next 7 minutes, we'll do separating words, and then there will be a bit of time for discussion after. And for ease, we omit constants and logs throughout the talk, so not everything will be completely precise. Okay, so take a string x in 0, 1 to the n, and we define a trace of x to be a random string formed by deleting each bit of x with probability 1/2 and concatenating the result. So here's an example of x in a random trace. So x is this top string, and the randomness is such that the first bit is deleted, the second and third are kept, the fourth is deleted, etc. And then all that's outputted is the remaining strings concatenated together. Okay, so what's the trace reconstruction problem? So there's an unknown string x of length n, and the question is how many independently drawn traces of x do we need so that we can determine x with probability at least 0.9? So here's an example. Here's the unknown string x, 0, 1, 0, 1, 1, 0, 1, and here are 5 independently generated traces. So this just happens behind the scenes. All we see is the resulting traces, 1, 1, 0, 1, 0, 1, 1, etc. So the point is, given these traces, we want to be able to guess the unknown string with high probability. And we want the answer for like a worst case x. So the answer is a function of n. Okay, I'm gonna have to skip some stuff for time reasons. Okay, so the first batch of bounds is 2 to the n and n. So for the upper bound, you can just wait until you see the whole string, right? Like if you have like e to the 1000 n traces, then like at some point you're going to see the whole string, and you'll know when you see the whole string because you know n, or you can deduce it from the lengths of the traces. And then this example gives a lower bound of n. And the main question is whether polynomially many traces suffice. Okay, and the trace reconstruction problem is essentially equivalent to its pairwise version. So if the unknown string is like truthfully promised to either be a certain x or y in 0, 1 to the n, then how many traces are needed to determine the truth? So we want the answer for worst case pair x and y. So let's do an example. So how many traces are needed to distinguish between these 2 strings? They each have length n. The first one is just 0, 1 repeated n over 2 times, and the second one is 1, 0 repeated n over 2 times. So the answer is actually just a constant. So you think about it, it might seem like kind of hard to distinguish between them. But what you can do is just look at the first bit of the traces. So if the true string was the top one, then you could do the calculation. The probability that the first bit is 0 is roughly 2/3. And if the true string is the bottom one, then the probability that the first bit of the trace is a 0 is roughly 1/3. So what you can do is you just look at all the traces, just focus on the first bit. If roughly 2/3 proportion of the first bit are 0, you guess the top one. And if roughly 1/3 are 0, you guess the bottom one. And with high probability, you'll be correct. And you can ask what happens if we always just focus on the first bit. So this, you can't just always do this. So if you have this string, this pair, for example, there's only an exponentially small difference in the probability of seeing 0 as the first bit. So e to n traces are required if you only look at the first bit. But for the same pair, if the ones differ, say at index n over 2 and n over 2 plus 1, then by looking at the n over 4th bit, you can distinguish between the strings with n to the 3/2 samples. So just to clarify, you get all these traces, you just focus on the n over 4th bit, count the proportion of those that are 1 and then over 4th bit, And you'll be able to guess the true string with high probability by doing that. So the probability of seeing 1 at index n over 4 if the true string is the top one is roughly n to the minus 3 halves greater than if the true string were the bottom one. So n to the 3 halves traces suffice. And what simultaneous work of Deodato Cervedio and of Nazarov Pera showed is that there's always some bit that you can focus on. Like this kind of algorithm of just focusing on only one bit always like works in a good way. So their theorem is that for any distinct x and y of length n, there is some index j, so that the probability that the jth bit of the trace is a 1 differs additively by e to the minus cube root of n. So consequently, e to the cube root of n traces suffice for trace reconstruction. And the proof uses complex analysis and analyzing Littlewood polynomials near 1. So it's really cool, but we won't have time for it. In 2018, Holden and Leons proved that n to the 5 quarters traces are required by considering this pair. So the point is, like, you have this defect 1, and it's the only difference, and you're just surrounded by a bunch of 0 1s, so it's hard to figure out where it is. Okay, so the second batch of bounds were e to the cube root of n and n to the 5 quarters. I did forget there was an upper bound of e to the square root of n proven at some point. Okay, so there's still a huge gap. And in 2019, we improved the lower bound to n to the 3 halves by carefully analyzing the same pair that Holden and Leons used. So it's the same pair essentially, and we just analyzed it better to show that n to the 3 halves are required. And n to the 3 halves is tight for this pair. Okay, and in 2020, nearly simultaneous work of Chen, De, Lee, Cervedio, Sinha, and of Narayan Ren published the observation that for a given small string w, few traces suffice to determine how many times w appears as a contiguous substring in the unknown string x. So let me explain what I mean by this. So for w equals 1, this fact is quite obvious. We can multiply the number of 1s that appear in the trace by 2, and this gives a good approximation to the number of 1s that are in x. But if we want to figure out the number of times 0, 1 occurs as a contiguous substring in x, this is much harder. So what one does is a weighted count of 0, 1 pairs in the trace, with a 0 occurring before the 1. So here's the scary formula. The point is, this is just something depending on the traces. The U denotes the trace. You look where the j0th bit is 0, the j1st bit is a 1, and for j0 less than j1, and you multiply by some weighting. But the point is that what you do with these traces, the expected value of this random variable is just the number of times 0, 1 appears as a contiguous substring. And so what the proof of e to the cube root of n did, they looked at a weighted count of the number of 1s. So they used a special formula, and it gave a weighted count of the number of 1s. So instead of getting an approximation to the number of times w appears, we get an approximation to a weighted count of the number of times that w appears in x. So if w equals 0, 1, we use this scary formula, where once again, this is just something complicated, only depending on the traces, and this is the number of times that 0, 1 appears as a contiguous substring in x, weighted by the position that it occurs at. And by doing some complex analysis, building off the work of Borwein, Erdely, and Kos, we can improve the upper bound to e to the 5th root of n. So that was the main theorem of part of the paper, that e to the 5th root of n traces suffice for trace reconstruction. So to summarize, the upper bound is e to the 5th root of n, and the lower bound is n to the 3 halves. So much more work needs to be done. Okay, I think I'm doing good on time. So the second problem is the separating words problem. So the basic object of study is deterministic finite automata. And this is one of the most basic computational devices. So here's an example of one. You have a bunch of states, Q0, Q1, Q2, Q3, and Q4. Q0 is the initial state, and Q3 and Q4 are accepted states. And the reason they're termed like that is it takes as input, this D of A takes as input a string X. It starts at Q, the state begins at Q0, and then it just reads bit by bit X and moves along the states accordingly. And we say it accepts X if it ends up at one of the accept states. So in this example, Q3 or Q4. So yeah, so the task that we're going to study with DFAs is telling two strings apart. So okay, this DFA, for example, accepts the string 0, 0 because you end up at Q3. It also accepts 1, 1, 1 and that. And it rejects the string 0, for example, because you end up at Q1, which is not an accept state. And similarly, it rejects 1, 0 in that string. And we say that a DFA separates X and Y if it accepts one, but not the other. So the above DFA separates 0, 0 and 1, 0 because it accepts 0, 0, but rejects 1, 0. Okay, so the question is, what is the minimum number of states a DFA needs to separate a given x and y of length n? So we asked this question for the worst case pair x and y. So the answer is just a function of n. And we restrict it to x and y of the same length because if they have different lengths, you can easily find a DFA that separates them with few states. So in 1986, Grosek and Quebec showed that any distinct x and y of length n can be separated by a DFA with a sublinear number of states. And they also showed a log n lower bound. So there exists a pair such that any DFA that separates them needs at least log n states. And then Robson came up with a clever argument improving the upper bound. So he showed that any distinct x and y can be separated by a DFA with n to the 2/5 states. And this bound was stagnant for 31 years, and we recently improved the n to the 2/5 to n to the 1/3. So any distinct x and y of length n can be separated by a DFA with n to the 1/3 states. Okay, so let's go over proof of an n to the 1/2 upper bound. It will give some intuition for the argument we come up with to improve to n to the 1/3. So the idea is to count modulo q the number of ones in positions that are congruent to I mod p for some I, p, and q. So you look at positions that are I mod p, you count the number of times you see a 1, and then you reduce this count modulo q. So we can do this with a small number of states. So you can have the states be z mod p cross z mod q, and you just keep cycling through z mod p. And every time you're at an index I mod p and you read the bit 1, you jump up a level in z mod q. So here's an example with p equals 5, I equals 2, and q equals 2. So the point is, so q equals 2, so you just have 2 copies of z mod 5, and you just cycle through them, except you go up a level, which for z mod 2 is equivalent to just switching. Every time you read a 1 when you're at an index I mod p, which is 2 mod 5. So down there. Okay, that's the idea. But let me explain how this leads to a nice mathematical problem. So let A and B be the sets of indices where x and y are 1, respectively. So let A be the set of k such that xk is 1, and let B be the set of k such that yk is 1. And for I and p in a set A, define AIP just to be the stuff in A that's I mod p. So the above idea can be rephrased as finding some I, p, and q with the number of things in A that are I mod p not being congruent to the number of things in B that are I mod p modulo q. And we want this, we want the number, and the number of states is pq. So just to rephrase it, we have distinct sets A and B, and we want to find some I, p, and q with pq small so that the number of things in A that are I mod p is not congruent to the number of things in B that are I mod p modulo q. And we can quickly get rid of the q, so I don't have time to explain why, but here is the problem we wish to solve. Let A and B be distinct subsets of 1 through n. How small of a p can we find so that there is some I with the number of things in A that are I mod p is different from the number of things in B that are I mod p? So taking the negation, we're asking for, just to get some intuition for the problem, we're asking for the largest p so that there are distinct subsets of n with the same number of evens and the same number of odds, the same number of things 0 mod 3, the same number of things 1 mod 3, etc. So it's a pretty natural question. And the answer is root n. So for any distinct A and B, there's some prime at most, some constant root n log n, and some I, so that the number of things in A that are I mod p differs from the number of things in B that are I mod p. And the proof is from the book. I'll just go through it quickly just to show that it's nice. I didn't discover it. So you look at this polynomial, the sum from k equals 1 up to n, and the coefficient is 1 if k is in A but not B, and -1 if k is in B but not A. So this is obviously a polynomial of degree at most n. And it has roots, under the assumption that the theorem is false, it has roots at e to the 2 pi I m over p. For all p less than big constant root n log n and m mod p. That's just because if you plug in a p3 of unity to the sum like basically decouples based on the residue of k mod p. And so the polynomial must be identically 0. It has degree at most n and it has all these roots. And by basic prime number estimates, the number of roots is more than n. Okay, so this proves a root n upper bound in the separating words problem. And what was our idea? Our idea was to count the number of ones. Okay, so the idea we just implemented was to count the number of ones in positions congruent to I mod p. Okay, so now I'm going to quickly rephrase this. So this can be phrased as counting the number of times 1 appears as a contiguous substring starting at an index that is congruent to I mod p. So you just look at, you look at when one appears, and you're just viewing it as a substring. So you're just see when one appears as a substring, starting in an index I mod p. So the reason we rephrased it in this obnoxious way is that it can be generalized to arbitrary strings w. So now we're going to count the number of times a certain string w appears as a contiguous substring, starting at an index that's congruent to I mod p. So here's an example of w equals 0, 1. Here's an appearance of 0, 1. It starts at index 1, which is 1 mod 2. Here's an appearance of 0, 1, but it starts at index 4, which is 0 mod 2. And here's an appearance of 0, 1, and it starts at 7, which is 1 mod 2. So if we do this, we come to the following problem. So a set is d-separated if any two distinct elements have difference at least d. So here's the problem. So let A and B be distinct n to the 1/3 separated subsets of 1 through n. And the question is, how small of a p can we find so that there is some I with the number of things in A that are I mod p is different than the number of things in B that are I mod p. So before the answer was root n, without the n to the 1/3 separated assumption. Now we're imposing an n to the 1/3 separated assumption, and we're wondering whether we can beat root n. And our main theorem for this is an answer. So for any distinct n to the 1/3 separated sets, there's some prime p of size at most n to the 1/3, with the size of AIP being different than the size of BIP. And the proof is complicated. It goes by some complex analysis, but it builds off an idea of Alex Scott for a closely related KDEC problem. So the upper bound is n to the 1/3, and the lower bound is log n. So still much more work needs to be done. Okay, thanks for listening. If anyone has any questions or anything.
Thanks a lot. So let's have some questions, put them in the chat, and I'll read them out. Okay, so the first question by Shachar Lovet is there a formal connection between these two problems?
If formal means like bound for one directly implies bound for the other, then no, I'm not aware of such a thing.
How about an informal one?
Well, yeah, I mean, I use the same kind of methods. The complex analysis was very close. So I think, okay, the right answer to this question is that there's a problem called the KDEC problem, which is like the information theoretic version of trace reconstruction, in which you want like two distinct strings to have the same subsequence counts for all small strings. And I think like both are connected to it. So I think that's the way that they're connected to each other.
Okay, thanks. Next question. Can you explain a little bit more how the proof of theorem 1 uses complex analysis?
No. So you should look at the paper of either Nazarov Perez or De Ozano Cervedio. Those papers are absolutely beautiful. The Nazarov Perez one is very short, but I can't just explain it now with words. And so, yeah, so the obvious question, what happens for longer patterns W? Oh, sorry, I skipped one. If we count the occurrence of W as a non-contiguous subword, is there any hope? Yeah, but yeah, you can do that, but it's harder to prove. So you can try that strategy. Some mathematical problems arise, but I wasn't able to like prove the necessary things. So the answer is like it probably does work in actuality, but proving that it works is hard. And for longer patterns W, so like there's a cost associated with using large W. So my like result, my n to the 1/3 result for separating words is completely tight if you use the substring method. If you balance the length of W with P and everything. So I think n to the, so for trace reconstruction, I like the pairwise version better. So I think, I mean, the pairwise and the normal problem differ multiplicatively by at most n, but I would say that the answer to the pairwise version is n to the 3/2, and the answer to the separating words might be log n. I mean, it might be that this is an extremal example. Okay, yeah, I mean, the example I showed might be extremal, so this kind of thing.
Wow, okay.
Yeah, so the X and Y, so you should think of like two Morse kind of words. Well, okay, so the X and Y that should be the worst case, my guess is that it's the example I gave that required n to the 3/2. But we currently cannot handle pairs that are generated by substitutions. So like the two more sequence and its complement are generated by like repeatedly substituting words, and there's more complicated substitutions that you can make that pop up in this related KDAC problem. So we don't know whether those pairs are actually hard, but we can't prove that they're not hard yet.
So what about the second problem? What is the right answer?
So I think it might be exactly this pair. So I think the answer is log n, and maybe this pair is the hardest. But I'm not an expert on the separating words problem.
So this might be a silly question. So for the trace reconstruction, what if you have a larger alphabet size? Does the alphabet size matter?
No, you can reduce, I think.
To the binary?
Yeah.
Okay.
Like if you have a bunch of letters, you can set one of them to be 0, the rest of them to be 1, and you figure out where the zeros are, that's where that letter is.
Yeah.
All right, but thanks everyone for the discussion.
All right, thank you. Let's thank Zachary again.
Yeah, hi everyone, thanks for coming. I'm going to talk about slightly improved approximation algorithm for the traveling salesperson problem, or TSP. And this is joint work with my amazing advisors, Karlin and Shayan, Oveis, Gharan. So in metric TSP, you're given as input a list of cities and their pairwise symmetric distances, which form a metric. And the goal is to find the minimum cost tour, which visits every city at least once. And this can either be phrased as finding the minimum cost Hamiltonian cycle, so like this, or as finding a minimum cost connected Eulerian subgraph, so like this. And these formulations are actually the same under the triangle inequality. And I'll work with this second formulation. So our problem is we're given a weighted graph, and we want to find a cheap collection of edges which connects the graph and gives every vertex even degree. And TSP is NP hard. So often we have to resort to approximation algorithms. And the best approximation algorithm has been a 1.5 approximation, and is due to Christofides and independently Serdyakov in the 70s. So this is a procedure which runs quickly and outputs a solution at most 50% longer than the optimal one. And unless P equals NP, we can't get an approximation algorithm which always gets within about 1% of optimal. So we have some work to do. But there's been a lot of amazing progress on TSP since this 3/2 approximation. And for example, we know a 1.4 approximation in the graphic case. So when this input graph is unweighted, and we even have a PTAS for low dimensional spaces. However, the general case has remained at 3/2. And I'm going to tell you about a tiny dent we made in this problem. So we proved there's a randomized 1.5 minus 10 to the negative 36 approximation algorithm for TSP. So yeah, pretty small number. But I'll start with 2 pieces of background and by defining the algorithm. First, this is the linear programming relaxation for the problem. So it asks for basically a fractional Hamiltonian cycle. So this means that every vertex should have degree 2, and every cut should have fraction at least 2. So this is a feasible solution. For example, here's a cut with value 2, and here's a cut with value 3. You can see no cuts have value less than 2, so this is feasible. And by value, I just mean you sum the x's of the edges that cross the cut. And this is known as the subtour elimination LP, or the Held-Karp relaxation, and it can be solved in polynomial time. And of course, this is a relaxation of the problem. So the optimal solution to this program bounds the cost of opt. And here's the second piece of background. So a spanning tree distribution is a lambda uniform if every edge has some non-negative weight, lambda e, and the probability of each spanning tree is proportional to the product of the lambda e's in its edge set. So this graph with lambdas 1, 1, and 1/2 would yield this distribution over spanning trees. And it was proved in 2010 by Sadpour et al. That for any point z in the spanning tree polytope, we can find a lambda uniform spanning tree distribution in polynomial time that matches the marginals of z. So in other words, if I give you any distribution of spanning trees, we can actually find another distribution that's lambda uniform and has the same edge probabilities. And they do this using a so-called max entropy convex program. So it turns out we can think of these lambda uniform distributions as the distributions which maximize entropy, subject to this constraint of matching the marginals of Z. And it turns out that lambda uniform trees have properties that are very useful for TSP. So here's the algorithm we study, which is up to some small epsilon from a 2010 work by my co-author Oveis, Gharan, and Sabarian Singh. So first you compute an LP solution X to this subtor LP that I showed you. And then you find a point Z in the spanning tree polytope such that Z of E is equal to X of E for all edges. It's not hard to do. Basically, the idea is that after a small transformation, the TSP polytope is actually inside the spanning tree polytope. So given this point Z, we find a lambda uniform distribution mu over spanning trees with marginal Z. So a max entropy distribution. And as I mentioned on the last slide, we can do this in polynomial time. And then we sample a tree T from mu. And since Z has the same marginals as X, this costs at most opt an expectation. However, T is not a TSP tour, right? Because it's not Eulerian. We have some odd degree vertices. So we just make it Eulerian. We add the minimum cost perfect matching M on the odd degree vertices of the tree. And so now our entire goal is just to show that the cost of the matching is a little bit less than half of opt in expectation. And since the tree costs at most opt in expectation, this would give a randomized 1.5 minus epsilon approximation. And I want to mention that Christofides' algorithm, this one from the 70s, is actually the same, except instead of selecting a random tree, it selects a minimum spanning tree. Okay, so the proof of this theorem consists of three main ingredients. The first ingredient is very combinatorial. So the LP solution X is just some two-edge connected graph. And it turns out that the cuts in this graph that are very close to 2, which we call the near minimum cuts because it's a two-edge connected graph, are closely related to the cost of the matching. And you can think of our matching as kind of spreading out across the graph to connect all of the odd vertices. And the near minimum cuts are really the ones that limit the movement of this matching. Unfortunately, there may be many near minimum cuts, so it's difficult to kind of deal with them all directly. And so in the first part, we reduce to so-called laminar TSP, in which these near minimum cuts, these important cuts, form a laminar family. In other words, they don't cross one another. The second ingredient is properties of max entropy trees. So it turns out that if you look at the multivariate polynomials encoding max entropy distributions, so they're generating polynomials, they have a nice geometry, which places max entropy trees in the class of so-called strongly Rowley distributions, which gives us a range of nice properties. So we use many of these properties and we prove some new ones along the way. And finally, we use these new properties to solve the laminar case with a kind of averaging argument. So to sum up, the first part gives us a well-defined problem to solve in the form of a laminar collection of constraints, like this collection here on the right. But these constraints are not always active. In particular, each constraint, which is given by one of the cuts in this family, is active when the tree that's sampled has an odd number of edges across that cut. So this second part gives us a range of properties about when these constraints are active. And finally, the third part uses that information to design a way to cheaply satisfy the constraints that turn out to be active. So that's the high level idea. And I'm going to start off by defining strongly Rowley distributions. So this ingredient in the center. So this is a class of distributions due to Borsea, Brandon, and Liggett. If you let mu be a distribution over subsets S of a set M, so for us, these are going to be trees over the edges of the graph, and let mu of S be the probability of a set S, then we say the distribution is strongly Rowley if its generating polynomial P of mu is real stable. Okay, so this is the generating polynomial. If you assign each element I of the set M a variable Zi, then you sum over all the sets in the support and you multiply their measure times the product of the Zi's for each element in S. And we call a polynomial real stable if it has no zeros in the upper half of the complex plane. So this just means that if I plug in, if I give all these zi's positive imaginary part, then if P of mu is real stable, the polynomial cannot be 0. And this is a bit hard to wrap your head around on a first viewing, but maybe for now, just notice that for univariate polynomials, this implies real rootedness, because in that setting, roots come in conjugate pairs. So you can think of this as a kind of generalization of real rootedness to multivariate polynomials. And as I said, any lambda uniform tree distribution is in fact strongly Rayleigh. This pretty much follows from the matrix tree theorem. And so if you take the generating polynomial of a lambda uniform tree distribution, you kind of zoom in on the univariate polynomial encoding the number of edges appearing in the tree in some set F. It shouldn't be too surprising that this polynomial is actually real rooted. So I know this is a bit fast, but basically I started with a real stable polynomial encoding my distribution over spanning trees. And this P of t is just some specialization of that real stable polynomial to a univariate one. So this P of t is real rooted. And this lets us apply an old and pretty amazing lemma about real rooted polynomials. It turns out that the coefficients of any real rooted polynomial with non-negative coefficients is identical to a sum of independent Bernoullis. So in our setting, this means that for any set of edges F, the random variable F sub t behaves exactly like a sum of Bernoullis. And more formally, I mean that for any set F, there exists some number of independent Bernoullis B1 through Bm, such that for any k, the probability that F shares k edges with a tree is exactly given by the probability these Bernoullis sum to k. And this gives us a really nice result. So if you apply this and do a simple computation, you can show that each near minimum cut, so each cut with fraction about 2 going across it, is even with probability at least 0.43. And so this is pretty cool. The existence of these Bernoullis actually lets us talk about parity, which would be quite difficult to study, I think, without this fact. Okay, so why am I even talking about parity? Well, remember that the matching is only over the odd vertices of the tree. So this should give you some hope. Since vertices are near minimum cuts, this says that about half the vertices should be even, and so only about half the vertices need to be in the matching. So this should sound promising. However, this is unfortunately not enough. So for example, we might even have 99% of the vertices even, maybe all but these two, but the two that end up being even could be really, really far apart. So this says something pretty strong, but we need something more. And we need actually that if we take a collection of near minimum cuts, not just one, with some constant size, that they're all even simultaneously with some constant probability. So one version of this is to say that if you take any constant number of vertices, then there's some probability that they're all even simultaneously. So to show this, we proved that if A1 through AK are disjoint subsets of edges, alpha of I is the expected number of edges of T in AI, and this alpha vector is close to the all ones vector, then with the probability that's a function of only epsilon and K, T has exactly one edge in all of the AIs. So in this example, it says that there's a constant probability that we get exactly one edge of each color in the tree. And this doubly exponential bound looks pretty bad, but there is some hope for improvement from recent independent work by Gurvitz and Leek, which you can actually hear about on Wednesday. And it turns out this statement is actually not a consequence of this theorem, hence this star here. But it would be true if the cuts we chose shared no edges. So that corresponds to this disjoint here. And we kind of muddle our way through in the paper and show that it's true enough of the time when the sets are not disjoint. But for the rest of the talk, just assume that this statement is true. Okay, so let's use this to do some analysis. So why do I keep talking about the near minimum cuts? Well, it turns out that the cost of the matching is the same as the cheapest assignment to these edges, which send fraction 1 across every cut that contains an odd number of edges in the tree. Okay, so this is actually very natural. You definitely need these constraints because if a cut has an odd number of edges in the tree, it contains an odd number of odd vertices, and definitely one has to be matched outside this set. And it turns out that these constraints are enough. And a feasible solution to this is going to be half of x, since the LP solution is a two-edge connected graph. And the solution costs half of x, or at most opt over 2. And now what I'll do is initialize my fractional matching to this feasible point, and then try to make it a little bit cheaper. So notice that my feasible solution has fraction 1 across every cut, because the LP has fraction 2 across every cut. But that's not really necessary, since we only need fraction 1 across the odd cuts of the tree. So what's going to be important to me if I want to make this a bit cheaper? Well, the constraints that are constraining me are the ones that are close to tight in this feasible solution. Everything else kind of has some wiggle room. And since this is half of x, the near tight constraints here are the same as the near tight constraints of x, or the near minimum cuts of x. So now how do I use this previous lemma about even near minimum cuts? Well, let's say that this picture on the right is my set of near minimum cuts. And what the previous theorem says is, for example, if I fix these 3 cuts, there's some chance I choose a tree where all 3 of them are even at the same time. And if this happens, so maybe if I pick a tree like this, then basically now we have 3 separate subproblems, kind of one for each of these green sets. And now we can find a matching inside each of the children. And now the edges that go across these 3 cuts will never be used. So in other words, I can just delete all of these green edges, which of course reduces the cost of the matching, and I can recurse on the 3 subproblems. So there are actually 2 issues with what I've said, and I'll quickly tell you about them. So the first is that the constraints that we care about might not look this nice. The near minimum cuts of x can actually look somewhat complicated, as in this picture on the left. And here it's not so clear how to define these subproblems. And so as I mentioned, we reduce to the case where these constraints look very simple. They just form a laminar family. None of them cross. And the second issue is this, so I kind of lied to you. If you get a parity structure like this, where these 3 cuts are even, if I delete all of these edges, what I get is not really a feasible solution to the matching in these subproblems. So let's say all these edges are 1/2 in x, and so they all begin at 1/4 in the fractional matching. Then after deleting these edges, this red cut only has 2 edges in it. So it has value 1/2. But since it's odd, it actually needs to have value 1 in the fractional matching. And so our solution will be to fix the broken constraints by increasing the value of some of these edges above their initial 1/4. So I'll increase these edges to 1/2 each, which will fix the constraint. And I'll do this kind of all the way down the laminar family, fixing all the constraints that deleting these edges may have broken. And this is a big component of our proof, kind of showing that this deletion and increase process favorably averages out. But yeah, this kind of, as desired, lets us bound the cost of the matching by a bit less than half of opt. And I want to mention that although this epsilon is very small, there's some quantitative studies that suggest maybe they're very good in practice, and so maybe we can do better. Also, recently we extended our result to show a bound on the integrality gap. This is on arXiv. And this also made our analysis a little more constructive, which should help in de-randomizing the algorithm, which is one open question. But the main open question is whether our analysis can be greatly improved. So we still have no idea actually how much better than 3/2 the algorithm is. And it's conjectured to be a 4/3 approximation. So we're very excited to see if more progress can be made. So thanks a lot.
Let's thank Nathan. Okay, so if anyone has any questions, we have about 2 minutes for questions. So please enter them in the chat. So there's a question: how complicated is the process of reducing to a laminar family of cuts?
Yeah, so it's not too bad. And one of the nice things is that it doesn't use these max entropy trees. It's kind of valid for any algorithm that samples a spanning tree from the LP solution. So it's very sort of combinatorial. And sort of the first thing you do is you delete cuts that are kind of crossed on both sides, like this green cut here, and then you kind of show that the remaining cuts have a simple structure. So it's a bit of a lengthy part of our paper, but it's not conceptually too bad. Yeah.
So this is joint work with John Fearnley and Rahul Savani from the University of Liverpool and Paul Goldberg from the University of Oxford. So let us consider the following optimization problem. Minimize a smooth function f over some bounded domain, for example, the unit hypercube. So there's a very good algorithm for this, which is called gradient descent, which simply applies this update rule repeatedly. So it's an iterative process, and it just applies this rule with a step size eta. The intuition behind this algorithm is very simple, namely that minus the gradient at some point corresponds to the direction of steepest descent. And so taking that direction gives us the best chance of improving our value, namely making it lower. So if we look at a picture, for example, this function f, if we start at the red point, then gradient descent could look like this perhaps. So just improving steps, taking us closer to a minimum. So gradient descent is widely used in practice, or perhaps some more advanced versions, but it's widely used and very effective, especially in machine learning. But from a theoretical standpoint, gradient descent does not actually solve this problem, this minimization problem. And the reason is that gradient descent is just guaranteed to output a stationary point, namely a point where the gradient is 0. Or to be more precise, because here we're working with in the constraint setting, it outputs a so-called Karush-Kuhn-Tucker point, a KKT point, which you can think of as just a stationary point with some special stuff if you're on the boundary. So gradient descent is only guaranteed to output a stationary point, and we can look at a simple example. What if we start gradient descent at the top of this hill? The gradient is 0, so we'll never get away. So gradient descent is going to output this point, which is not a minimum of the function. It's not even a local minimum. In fact, it's the opposite, it's a maximum. So gradient descent does not solve this problem, this minimization problem. And from point of view of computational complexity, we know that this minimization problem is hard. We know that it's NP hard, and even finding a local minimum is NP hard. And so the question that we ask ourselves in this paper is, okay, but what is the complexity of the problem that is actually solved by gradient descent, namely the problem of finding a stationary point? And there are many ways to reformulate this question. For example, we can say, what is the complexity of finding a gradient descent solution? Or in other words, what is the complexity of finding a point where gradient descent terminates? So this is the computational problem that we study. And of course, in order to study it, we have to somehow define it formally. So we consider the following problem. The input is a continuously differentiable function f, a step size eta, and some precision parameter epsilon. And the goal of the computational problem is to find a point where gradient descent terminates. And of course, we have to define what that means exactly. And there's many ways to do that. And there's at least two very natural ways that we consider. So the first one gives rise to a problem that we call GD local search. And here we say the goal of the problem is to find a point x, such that the next iterative gradient descent, which we denote x prime, is such that the value improves by less than epsilon. So the improvement that we see by doing one extra step of gradient descent is very small. In that case, such a point x is a solution of a problem. Another way to define when gradient descent terminates is to say, no, actually, gradient descent terminates when the next iterate is very, very close to the current one. So in that case, you get this problem GD fixed point, where the solution, point x is a solution if the next iterate x prime is epsilon close to x. So these are two ways to define this gradient descent problem. And fortunately, it turns out that they're polynomial time equivalent. So it doesn't matter which one you pick, which one you prefer, the complexity is going to be the same. And the reason for this is that the underlying fundamental problem is this problem of finding a stationary point, or a KKT point to be more precise. And as a result, there is a robust way to define this gradient descent problem. So I won't give you the fully formal definition of this problem, but let me just mention that we study the problem in the standard Turing machine model, which means that the function f has to be given to us in some white box manner. And so, for example, it could be given as an arithmetic circuit. That'd be one way to formalize this. So we saw that the actual minimization problem is NP hard. And so a natural question is to ask, is this gradient descent problem also NP hard, or is it easier? And to answer this question, I need to define a class. So the class TFNP was defined by Megiddo and Papadimitriou 30 years ago, and it contains all total NP search problems. So what are these total NP search problems? First of all, they are search problems. Namely, we're looking for a solution, not just a yes/no answer, so it's not a decision problem. Then they are NP search problems, which means that if I give you a candidate solution, you can verify in polynomial time if it is indeed a solution or not. And finally, they are total, which is perhaps the most important property. Namely, for any instance, there always exists at least one solution. So let's take a look at some examples. The first example is factoring. Given a number, compute a prime factorization of that number. This is a TFNP problem. Another one, a problem from game theory, is Nash. Given a game in strategic normal form, compute a mixed Nash equilibrium of the game. This is guaranteed to exist by Nash's theorem. And finally, our gradient descent problem is also a TFNP problem. And why is that? Well, clearly it is a search problem. We can verify solutions efficiently because we just need to check this termination criterion, the stopping criterion. And finally, it's total. Why? Because our domain is bounded. So because the domain is bounded, it's guaranteed to be a minimum, and any minimum is in particular a gradient descent solution. So this class TFNP is quite interesting because it lies between P and NP, or rather the search versions of these classes. And it contains many problems that are believed to be hard. And of course, as theoretical computer scientists, we would like to be able to provide some evidence that these problems are really hard. So the standard thing we might want to do, which is to show NP hardness, unfortunately, it doesn't look like this is going to work because no TFNP problem can be NP hard unless NP equals conp. So this essentially means that NP hardness is off the table. What's the next best thing we could hope for? It would be to prove TFNP completeness. But here, because of how general this class TFNP is, we don't believe that it has complete problems at all, actually. So that seems also like a doomed approach. So what can we do? What Papadimitriou proposed around 30 years ago is to define subclasses of TFNP, syntactic subclasses, which have complete problems, understand how these classes relate to each other, and classify the computational problems that we care about in terms of these subclasses to understand which ones are harder and which ones are easier. So there are various classes. There's a class called PPP, which is based on the pigeonhole principle. There's a class called PPA, which is based on parity arguments, like, for example, the handshaking lemma. And then there are two very successful classes. The first one is PLS, which essentially contains problems where the totality follows from a local search argument. And there are many local search optimization problems that have been proved complete for PLS. And an example is local max cut, which is in a graph, find a cut that is maximal up to some local changes. So PLS is very successful, and another very successful class is PPAD, which you can think of as the class of all problems where totality, so existence of a solution, follows from a topological fixed point theorem, which is called Brouwer's fixed point theorem. And famously, the Nash problem is PPAD complete, but there are also many other problems from game theory and other application areas that are PPAD complete. So this is a partial picture of TFNP. And so going back to our question, where does our gradient descent problem lie in this picture? And so it turns out that it lies here, namely both in PPAD and in PLS. And let's zoom in to give a brief explanation for why it lies there. So remember, when I talked about the gradient descent problem, I gave you two potential definitions, which were equivalent, but they were still quite different. So the first one was this fixed point definition, where we thought of it as the termination criterion being the next iterate is close by. And totality of this problem can be proved by using Brouwer's fixed point theorem. And as a result, this problem lies in PPAD. If you consider the other variant of the problem, GD local search, there it essentially immediately follows that it has to have a solution by a local search argument. And as a result, you can show that the problem lies in PLS. So what you get is that these two versions lie in PPAD and PLS, and since they're actually equivalent, it means that the gradient descent problem that we care about lies in this intersection. Now, this intersection of classes, it has been studied before, namely by Daskalakis and Papadimitriou 10 years ago, where they noted that actually a ton of interesting natural problems lie in this intersection. And so let me just give a brief list. The problem of finding a fixed point of a contracting map, the problem of finding a mixed Nash equilibrium of a congestion game, the problem of solving a P-matrix LCP, which is a generalization of linear programming, the problem of finding a fixed point of a Tarski function, the problem of solving simple stochastic games, and more. So they noted that all of these interesting problems lie in this class. And they also noted that PPAD intersection PLS seems like a very unnatural class, and so was unlikely to capture the complexity. So let me briefly explain why this class seems so unnatural. So take any PPAD complete problem A and any PLS complete problem B, and define the following problem, either solution of A or B, which is simply, I give you an instance of A, an instance of B, and I just tell you solve one of the two, whichever one you want. I don't care which one you solve, I just want a solution to one of them. So essentially straightforwardly follows that this problem is automatically PPAD intersection PLS complete. So that's great. There's a complete problem for the class already. The problem is that these are the only complete problems that we know, and they are extremely unnatural and artificial. And so as a result, this class, it seems like a very artificial, unnatural class, which is unlikely to exactly capture the complexity of these natural interesting problems. And so Daskalakis and Papadimitriou defined a subclass of PPAD intersection PLS, which they call CLS for continuous local search. And they showed that a lot of those natural problems actually lie inside CLS, which provides additional evidence that these problems might be CLS complete, that CLS might be the right class to capture their complexity. So now going back to our problem, gradient descent. Gradient descent is essentially just a special case of continuous local search, which means that the gradient descent problem lies in CLS that's relatively easy to show. And so the surprising result that we show is that gradient descent is not only CLS complete, but in fact, PPAD intersection PLS complete. So what that means is that we provide a reduction from this weird, unnatural, artificial either solution problem to the gradient descent problem. So we construct in polynomial time a smooth function f, so that any stationary point of that function gives you either a solution to the PPAD complete problem A or a solution to the PLS complete problem B. And now this completeness result means that there's a collapse here, namely that PPAD intersection PLS is the same as CLS, and it has this nice, interesting complete problem gradient descent. And this collapse has some consequences. So the first consequence is that, as it turns out, PPAD intersection PLS is an interesting class, surprisingly, and it has a very nice characterization in terms of continuous local search and even gradient descent. So you can think of PPAD intersection PLS as containing all problems that can be solved by gradient descent, which is a very natural characterization. And there are also some technical consequences about CLS, because we essentially show that the two-dimensional version of continuous local search or even gradient descent is as hard as the high-dimensional one. So let me finish by just mentioning some future directions. So the first one is other intersection of classes that are interesting, because you have these two interesting classes, PPAD and PLS, and somehow their intersection turns out to be something very interesting and natural. Other examples of this phenomenon. And the second point, of course, is to find more problems that are complete for PPAD intersection PLS. And I've put some candidates here. The contraction problem, find a fixed point of a contracting map. find a fixed point of a Tarski map, find a mixed Nash equilibrium for congestion game. And actually that last problem has been solved. Namely, it was shown by Babichenko and Rubinstein at this talk that our gradient descent problem reduces to the mixed congestion problem, which means that the mixed congestion problem is also complete for PPAD intersection PLS. So make sure to check out their talk if you want to find out more about this. And let me mention one more paper at this talk, which is related, which is by Daskalaitis, Koulaitis, and Zapataitis, where they consider a more general problem than the minimization problem that I had on the first slide, which is called the min-max optimization problem. And they study a related question and show that there, it turns out that the problem is PPAD complete, so harder, which reflects the fact that min-max optimization is harder than min optimization. So that's it for my talk. Thank you for your attention, and feel free to come by the poster if you have any questions.
Let's thank Alexandros. So if you have questions, put them in the chat and I'll read them. And there's already 2 questions, or actually 3 or 4 there. So the first one is, does it matter how the input function f is encoded?
Yes, that's a good question. So our result is about the case where it's an arithmetic circuit. But actually from the result of Babichenko and Rubinstein that I mentioned at the end, it follows that the problem remains hard even if the function is just a polynomial that's explicitly given to you. So even if I just write down a polynomial, even the problem remains hard even in that case, which is a very natural way to represent a function.
So the next question is, can you say anything about the version of gradient descent in which the step length eta is chosen optimally in each iteration, say by a line search?
So I cannot say anything directly. What I can say though is that this gradient descent problem that we consider is equivalent to the problem of finding a stationary point, or more precisely a KKT point. So our hardness result applies to the problem of finding a KKT point. So if your method just does not do better than finding a KKT point, then the hardness result continues to apply.
Thanks. Okay, the next one is, how relativizable is the result about the coincidence of classes?
Yes, so the reduction, even though I presented it here in the white box setting, because that's where CLS and all these classes are mostly studied, the reduction is actually a black box reduction. So it also holds if you consider the query versions of these problems. So you can define a query CLS, query PPAD intersection PLS, and the collapse holds there as well.
Okay, thanks. Okay, and then the last one is, can you say a bit about the reduction techniques and tools?
Yeah, so I guess there you have to come to the poster. I have a few pictures there. But yeah, the idea is that we reduce from a PPAD complete problem, which is called end of line, which is essentially find the end of a line where the line might be very long. And the idea is that we can embed this line, but when it takes a bad turn, that's a problem for us. And that's where we embed the problem B, the PLS problem, in order to have a solution of the PLS problem embedded there. So that any solution gives us either a problem to the end of, either a solution to the end of line problem or a solution to this PLS complete problem B. And I have a few pictures in the poster.
Great. Okay, any more questions? Okay, if not, let's thank Alexandros again.
So thanks everyone for attending this talk. Today I'm going to talk about indistinguishability obfuscation from well-founded assumptions. This is actually a multi-year close collaboration with my wonderful co-authors Rachel Lynn and Amit Sahai. Let's start off with a really basic question, and the question is the following. What you want is a way to take in a source program or like a code and turn it into an unintelligible version, as unintelligible as possible, while at the same time preserving its input-output behavior. So just to make it formal, this problem is called as program obfuscation, and it was for the first time
coined in this Turing Award work of Diffie and Hellman. So what were they asking? They were asking, can you come up with this compiler, which I'm going to call as obfuscator, which, by the way, is a polynomial time machine. It takes as input a source program. You can think of it as a C code, a Java code, or in some mathematical model like Boolean circuits or Turing machine. Takes as input that, outputs another one. Now this resulting program has essentially the same input-output behavior. It's at most polynomially slower, but more importantly, it reveals minimal information about the initial program. So what does this mean? Like it needs to be as unintelligible as it can be, provides best possible notion of protection. So I'm not going to make this precise yet. I'm going to only tell you about what it really means, minimal information in this notion. For the time being, let's just keep it abstract and see what all it can be used to build. So I'm sure if you think about it, such a natural notion, it shouldn't be really hard to come up with some nice application. In fact, the first work that ever proposed it was Diffie and Hellman's work. There they had an extremely natural application. Back then, they were trying to build public key encryption schemes, and they had a very natural approach using this obfuscation to build a public key encryption scheme. Their idea was, why don't we simply obfuscate a program that takes as input a message X and outputs, and it has a key K for a secret key encryption scheme hardwired, and simply output an encryption of that message with that key. Okay. Now, what's the point? The point is essentially this now becomes like a public key, because having access to this, anyone can encrypt any message of their choice, right? The hope was that since this obfuscation scheme is going to provide this best possible notion of security, it's going to hide information about the secret key of the secret key encryption scheme, so that the security still holds in the presence of this obfuscated code. Okay. Now, to make all these arguments work, you have to be really, really careful. You have to define these notions carefully. I'm not going to do it until later on in this talk. Let's just keep it abstract. Just try to see what all it can be useful for. However, as I was saying, building something as basic as public key encryption is really like using a sledgehammer to crack open a nut. Let's ask ourselves some more real-world question, what all you can use it for. You can, for example, do software protection. So let's say you have a piece of software which has some trade secrets, intellectual property, and all of that inbuilt inside the piece of the software. You could use your obfuscation to obfuscate this code. And now the point is, anyone wants to use it can still use it. At the same time, since this obfuscated code provides you the best possible notion of security, you're going to get the best possible protection for your software. Similarly, you can think about obfuscating machine learning classifiers. The way these machine learning classifiers are built, typically they are built by training on huge set of sensitive data. And if you reveal these classifiers in the clear, you're going to compromise the integrity of your sensitive data. Now, if you had obfuscation, you can also obfuscate the classifier. And the point is, someone wants to use it can still use it. At the same time, you're going to get best possible guarantees from it in terms of protection for the data. But you can also do other things like hosting services on the trusted cloud. And today, the notion of obfuscation that we consider, which is called as indistinguishability obfuscation, which is the subject of my talk, it's known to imply most of the cryptographic primitives that exist out there today. So it's a really versatile tool. So once we have seen applications, let's now dive into the history of this problem. So as I was saying, for the first time, it was coined in 1976 as a problem. But then for next 25 years or so, there was actually a period of silence. But then in 2001, there was this work of Barak et al., which actually gave the first mathematical treatment to this question. And they had two really invaluable contributions. Their first contribution was that they looked at this extremely natural definition, which was the de facto notion of security, called as virtual black box security. Now, I'm not going to define what this really means, but that's what they were studying. This was like the standard notion of security. Unfortunately, they proved that it is impossible to build an obfuscation scheme satisfying that virtual black box notion of security. So it was really seen as a huge negative result for this question, and actually instilled in the community a bit of pessimism about this question. However, at the same time, they actually also gave us a slim ray of hope. So they defined this new notion called indistinguishability obfuscation, which was also a very natural notion, but it seemed much weaker than black box security. So it wasn't even clear if it is any useful at all in real world applications. And they didn't even know how to construct it. So kind of everything, including the analysis of this notion, was left open back then in 2001. So this was the state in 2001. And by the way, throughout this talk, I'm not going to call it indistinguishability obfuscation anymore. Just to keep our life simple, I'm simply going to call it IO, just because it's difficult to pronounce. So this was 2001, and then again, there, just because of the pessimism of the negative result, there was again some silence. But then things changed in 2007. In 2007, there was a work which kind of analyzed this definition and actually showed that this notion provides best possible notion of security that you could ever hope for. So it was really like not as bad as we were thinking about indistinguishability obfuscation. And then, community picked up and there was a lot of progress on two fronts. The first front was, of course, like use cases for indistinguishability obfuscation, what all it's useful for. And then we figured out that, it's useful for building, by the way, on this slide, I'm going to list some, cryptographic primitives. If you haven't heard about them, that's totally fine. I'm just trying to demonstrate that it's really useful. So we realized that, using indistinguishability obfuscation, you can build not only classical cryptographic applications that we know anyway how to build, but actually it opened up a whole new brave world for cryptography. Almost all known applications that we know today can be built from IO. And some of these applications were not even considered before IO was popularized as a concept, because the kind of guarantees that they were asking were just too much, and people didn't think that they were, it was likely to build such a thing. So IO was really expanding the scope of cryptography. And it's for this versatility, it is really a worthy goal. And in order to realize that, actually, we did a lot of work in the constructions point of view also. So people started taking this question really seriously, and there was actually a lot of work. On this slide, I've listed down some of the major construction paradigms, some innovative cryptanalysis that also came along. So really a lot of work. Unfortunately, however, in all of these constructive works, there was typically one of the three main problems. The first problem was that most of the time the construction was heuristic in the nature. So it was like, here's the construction of this obfuscation scheme. And it was just conjectured that this construction is secure. It was just like saying, here's the construction and believe me that this is secure, which is totally unacceptable, because when you think about cryptographic primitives, you want, sound guarantees. You want that, they should be as hard as solving some well-established hard mathematical problem. You don't want to take a leap of faith here. So that was about heuristic security, which is unsatisfiable. But some of the times, actually, we did make some efforts, and we were able to identify some new problems. So a problem on which you can rely security for the obfuscation. However, at the end of the day, it was a new problem designed specifically for making the proofs go through. And therefore, our community cryptanalysis and the algorithms community hadn't looked at that problem for a long time. So our confidence in those assumptions were really low. But more importantly, actually, and more in a disappointing manner, there was actually cycles of attacks and fixes in both these in cases. Actually, so there was a construction which was broken, which was fixed again, and this cycle kept happening and happening. Because of this, our confidence further lowered. And at that time, it wasn't even clear whether this you can ever base indistinguishability obfuscation on well-studied hard problems. So what we want to do, we want to construct an IO scheme which is as hard to break as some long-standing mathematical problem which we have looked for a long time. And this is exactly the status. This is exactly the topic of this talk. So before I tell you actually the main results, let's now finally see what indistinguishability obfuscation is. So this is indistinguishability obfuscation. Well, it's just an obfuscation scheme where you have guarantees which say that it's going to protect implementation differences between the two programs. So let's make this precise and see what it is. So let's say you have two programs, pi and lambda, and they satisfy this premise of being functionally equivalent. What does that mean? So let's zoom in on it. It essentially means that these two programs have same input-output behavior. meaning on every input, you get the same output in both these two programs. And we also have some common sense requirements for this. So those requirements are basically that the running times of these programs need to be the same, and the description size also need to be the same. And usually these two things are never a red herring, because if you consider any two programs of interest, typically you can make their running time to be the same by making them run for extra longer. You can also make their description size to be the same by padding them appropriately. Okay, so what we essentially want is that their input-output behavior is the same. Now, what could be different? The internal workings or the implementations of these two programs, how they are actually implemented, those can be totally different. So what does IO says? It says that if you have two programs which have the same input-output behavior, but otherwise implemented differently, then if you obfuscate the two, you wind up getting two programs which are actually hard to tell apart or distinguish by any polynomial time adversary. Okay, so that's the kind of guarantee it gets. And just to give you an example, you can think of pi as being a bubble sort program and lambda as being a selection sort program. Now we know that both of these are sorting programs. They do essentially the same thing, which is to sort array. What is different? The actual code, how they are written is different. And IO is going to guarantee is that if I obfuscate bubble sort and give it to you, you won't be able to tell me for sure whether it was bubble sort or selection sort or some other sorting process. So that's the kind of guarantee. Now, at this point, it may not be even clear why is this this kind of guarantee of just protecting this kind of implementation differences is enough. Unfortunately, that's a really subtle point. I won't have time to talk about it. But really, the idea is that we cryptographers have figured out that somehow in the proofs, this is always the kind of guarantee that is needed for making those applications work, and that's why it's so useful. I can talk offline about it. So this is why this is IO. So here is our main theorem finally. What we show in this work is that you can construct indistinguishability obfuscation whose security rests upon hardness of 4 well-studied cryptographic problems. Put another way, there are, think of it as there are 4 well-studied cryptographic problems which have been there for a long time. People have looked at it. The people from algorithms community and cryptanalysis community have looked at them carefully, and what it means is that we construct an explicit indistinguishability obfuscation scheme, which is secure as long as all those 4 cryptographic problems are indeed hard. Okay, so it kind of rests upon all those 4 problems. Unfortunately, I won't have time to tell you what exactly these problems are, but I can at least name drop them here. But the key point is that these problems have been introduced in cryptography about 15 years or so, but they're actually very well rooted in various other branches of computer science even before that. So one of the problems we are using is existence of Boolean PRGs in NC0, which actually has its roots in complexity theory from the domain of constraint satisfaction problems. Another problem we are using is elliptic curves, which goes back to the days of Andre Weil and Victor Miller. So it's a number theoretic problem. Another problem we are using is LPN over ZP, which is related to the age-old notion of decoding random linear codes with sparse noise encoding theory. And finally, one of the more popular problems, the learning with error problems, which is very well rooted in lattices. Okay, and it's famous for especially constructing homomorphic encryption. So these are the 4 problems, and this is our theorem. Now let's see how we actually do it. Like unfortunately, I of course won't have time to tell you all the details. But let me give you a couple of things. So on a really high level, we actually follow an extremely simple principle of divide and conquer. We break down the task of constructing this complex primitive into simpler and simpler problems, and then we solve each of them and then tie them somehow into a solution for that. And as I was saying, it was actually a culmination of a multi-year effort where the precise goals were exactly to identify which problems to consider and solving them. And in this work, our contribution was exactly to identify one missing crucial piece, which was related to the notion of simple pseudo-random generators. And I'm going to tell you about that in the next few slides. Okay, so we study this so-called simple pseudo-random generator. We then construct them from well-studied hard problems, and then that gives us the rest of the solution. Okay, so let me now recall this notion of pseudo-random generator. I'm sure you have seen it in some phase in different contexts. So what are pseudo-random generators? Well, They're extremely simple Boolean functions. By simple, ideally, they are in constant depth Boolean functions, so NC0 functions, right? And they take n bits of inputs for some n, and they output m bits, where m is like some polynomial in n, so really expanding. Think of it as n to the 1 plus omega of 1. Okay, and they're extremely simple. They have a really extremely natural property. The property is that if I evaluate this Boolean function g on a random input sigma, the output is going to be indistinguishable to any polynomially time bounded adversary to a truly random string which is sampled from this larger domain 0, 1 to the n. Okay, so that's the kind of intuitive guarantee. Now, these are extremely natural a notion pseudo-random generator. It's like extremely well studied in different communities. So a really natural question is, how simple can a PRGG ever be? And again, by simplicity, I really mean its degree when I write down this function g as a polynomial over the integers. So I'm really asking for the Fourier degree or the multilinear degree, and how small can it ever be? The reason I'm asking this question is because if somehow magically I'm able to construct a degree 2 PRG, a PRG g which can be written as a degree 2 polynomial over the integers, then it was already known how it can imply IO. Okay, so the problem would have already been solved. Unfortunately, PRGs with degree 2 with a polynomial stretch can simply not exist. There are actually explicit algorithms which break any arbitrary PRG set satisfying degree 2. Okay, so that was the state of affairs before this line started. So one of the things that we considered in order to bypass the impossibility was a really natural extension. We cannot achieve anything with degree 2 PRGs. Can we realize degree 2 PRG in a pre-processing model? So here was the model. Now we were asking, can I pre-process this input sigma into another input sigma tilde such that now I require that this PRG is evaluable by a degree 2 polynomial on this new input sigma tilde. Okay, that's what I want. Now, if you think about it, this question doesn't even make sense if there's no bound on the length of sigma tilde, because you can trivially pre-process all the monomials that ever exist in the in the computation of g of sigma and trivially get a degree 2 PRG like that. So we also have this requirement that the size of sigma tilde is only sublinear in the output length, okay, m to the 1 minus epsilon. So the question is, can you construct such a PRG? And first we have to ask whether such a PRG is useful. And indeed, we figured out that over time that actually if you could build that, that will also suffice. But here again, there was a lot of implausibility results, and it was heavily infested with those negative results. And as a consequence, this was the state before this work. What we identified is that you can bypass this further, and we propose another model, which is kind of useful to construct IO and then construct such a PRG. So this is our final model, which we call structured seed PRG. It's another different kind of preprocessing. Here, we require that you have this string input sigma. Now we are allowing it to be preprocessed into 2 strings as opposed to 1 string. So one of the strings is called P, the other one is called S, and both of them are vectors over ZP. Okay, and again, we have the size requirement that it's sublinear in the output length. Here, P and S have different meaning. P stands for public, so it's going to be revealed to the adversary, and S will be kept hidden. So this is the short preprocessing. And now there's another kind of degree 2 requirement. We want that the PRG is evaluable by a polynomial, which can be a constant degree polynomial as opposed to a degree 2 polynomial, as long as its degree in the secret part, S, that's going to be degree 2. It cannot exceed more than degree 2. Okay, so somehow we're asking at the cost of having another public string, can I reduce the degree of the computation to degree 2? Okay, and this was what we were asking, and it has a really extremely natural security guarantee. We're asking, can I ensure that given P, which is the public information, G of sigma is indistinguishable to random? Okay, so it has pseudo-randomness property. So that was the entire SPRG. So we show in this work that this kind of notion is enough. And not only that, we actually construct it from well-studied hard problems, including the hardness of decoding random linear codes with some random sparse error with some parameters, and PRGs in NC0, which is also a very well-studied hard problem. Okay, unfortunately, in this talk, I couldn't go over a lot of details. I'm going to refer you to this link, which has all the details for this thing, and I'm looking forward to talk to you in the poster session. And if you have any question, you could also write to any of the authors.
Okay, let's thank Aayush. So we have maybe 1 or 2 minutes for questions. So if you have any questions, you can enter them in the chat and maybe Aayush can respond. Okay, well, if there's no questions, maybe you could join Aayush at the poster session. And I would like to thank all the speakers in the Best Student Paper and Best Paper session today.